Hello. So let's get started. I'm Leo from Linea Consensus, and today's talk is about how to test zkEVM prover. So especially we have kind of a framework to test or stress test zkEVM prover internally. So I would like to introduce how we test it. So this is the agenda today. So I'll talk about the problem or why we built this framework, and we'll talk about what's the difficulties in zkEVM testing, and we'll share the details about our stress testing. So what's a hot news right now? So I mean, Linea is now 100% proven. You can go and check our Twitter. So we've been working on this for almost 6 years, and finally we are 100% proven. And we are still zkEVM, and we have no plan to move to zkEVM yet. But another news is now everyone is talking about zkEVM, right? So zkEVM versus zkEVM projects are moving to zkEVM. So last year, I guess in DevCon or some other conferences, we had many zkEVM friends or projects. Right now, they're talking about zkEVM. So why is that? So is building zkEVM hard? Yes. And is it direct arithmetization difficult? Yes. But we think zkEVM is more efficient. So it's yes. But what about how many projects are working on zkEVM? We are not sure. Maybe we are the only one, or we have some friends. So the biggest problem here is that we have many challenges in building zkEVM. One of the problem is we are lack of standardized testing tools and best practices. So no one shared how they test zkEVM. So when they build or implement their constraints and also their prover, because most team they have internal custom test infra and they never share this infra, and now they are working on zkEVM, so I thought it's good to share our experience today. And there are many edge cases when you are testing constraints and prover, so it's difficult to control or manage. So we will also cover today how we manage that. So these two challenges will be today's topic. But the other challenges, like direct arithmetization of the EVM, is very hard, because you need many PhDs working on it, solely working on it. And also, whenever there is EVM upgrades, you need to modify or update your constraints again. So these challenges, we are dealing with these challenges by introducing a high-level language for constraints, but this will be covered in another talk. And today I will focus on how to test zkEVM. So what are some best practices? So how the heck do you test this stuff? We really don't know. So maybe some project, maybe they don't find any other options and just go test in production. This actually happens. I'm pretty sure this actually happens. And many projects, they just, tonight we test in production. It could be mainnet or in testnet. So I guess many projects, they used to test their new constraints or prover version in testnet because it's easier. You just deploy it and you waiting for some errors or incidents and you fix it, right? But that is also bad idea because your users are using testnet anyway. So the goal of this talk is we are going to share our experience on continuous integration and testing of zkEVM. To help other teams, if there's any, and to avoid their mistakes in testing it. And because it's beautiful and it's nice weather, so I'm not going to share any technical details today. Yeah. So let's go to look at our testing environment. So we have a kind of multi-layer testing infrastructure. So let's say we have I simplified it, and so we have 3 layers. The first one here is about how we test constraints. So we have this constraint unit test phase. So here we only focus on implementing constraints based on our constraint spec, and we write unit tests, and especially we focus on covering edge cases. I will go detail in the next slides. And when we finish this phase, we move to the other phase, and this is the main phase actually, the stress testing. So here we are running many provers and many best nodes, and we are generating the traces, the trace files, and then we use it to stress test the prover before we move to DevNet, Sepolia testnet, or mainnet. So let's cover one by one. So the first thing is constraint unit testing. So unit tests here, we cover constraint unit tests. These are the toughest one, I guess. So here what we do is we write unit tests for constraint in general. So the spec. And especially we found out that when you cover only these general constraints, you will see a lot of errors. So we especially focus on writing edge cases, writing unit tests for edge cases and boundaries or abnormal behaviors especially. So we are writing thousands of unit tests for only edge cases. So for example, this is the left side, we have this general case unit test. So when you to check valid balance. So you can spend some balance or amount, gas, something like that. But those edge cases will cover zero value transaction or maximum value transaction. This, in reality, you won't see this that often. But for testing, we are covering all of these edge cases as much as possible. So after this phase, we move to the next unit testing phase. This is called constraint replay test. So we have this repository. When you go here, we have this function called replay. So this one is when you write a unit test, you can actually generate a trace out of this unit test. So when you look at the diagram, we can actually get those trace files from edge cases unit test, and then we run this constraint checking tool to see if those traces satisfy our constraint spec. So if it fails or pass, we make a kind of a feedback loop, and we do it again and again and again, and we cover tens of thousands traces before we move to the next phase. So if we finish the first phase, the next phase is harder. So the next phase we are actually running the prover, and we are actually using some basic infrastructure solely designed for our testing. So let's move to the first infrastructure, which is called shadow environment. We call it a shadow environment because it kind of a clone of our production environment. So when you look at there, we have when you look at there, we have Sepolia and mainnet environment. Those are version, for example, 2.0. And we are actually deploying these Sepolia or mainnet Bezus in our testing environment. So it's a kind of a copy-paste, and we keep syncing those traces. But we deploy different versions of tracer, Bezu, or a state manager, and so on. So whenever we need to move to the next release, we deploy different versions of this actual infrastructure, and we reuse it to test our prover and constraints and everything. So by using this shadow environment, we can actually run those testings. So in this testing, we run prover, the real prover, and we can test our constraints, and we can also test Bezu tracer or some errors in state manager and so on. So for example, we have this execution prover here, and we have this as an input. We have these conflation ranges. This is from the real environment. So we can test any conflation range from Sepolia or mainnet. We have historical ranges, or you can focus on some specific ranges when there was a TPS, a high TPS, or some incident or something like that. And whenever you can send a request to the tracer from the shadow environment, and then you will get a trace for a specific version of a release, so that you can run this prover with these traces and with this specific version of constraints. So when you find these errors or some problems, we send this feedback to the arithmetization or constraints team or best team, depends on the errors, and then we make an update and we redeploy the shadow environment again, and we keep working on the test. So when I talk about the testing ranges, I said maybe we can test the historical ranges, because when you go to the Explorer, you can have those historical ranges already. But what we found out is that when you randomly test your traces, it's not that efficient, because as you can see here, we had this transaction TPS, and this is Ethereum, and this is the pink one is Linea. And sometimes we have higher TPS than Ethereum. So in this case, we had a kind of events during this time. So when I test some traces around this area, so the trace size is very small, and there are not many OP codes or operations used. So it's not efficient enough when you have limited time of testing. So in this case, you can just focus on very specific areas like this area, and then they will have very large trace size and a lot of operations there, and very dynamic user activities there. So that's what we found. And when we tested, actually, we run 3 types of testing. So one is just random access, and the other one is we run over the latest, the real time right now, the live transactions, and also on these historically very transactions with very high activities. I will also talk about how we scaling out our testing environment. So here, here each testing node, the prover testing node, has 10 terabytes of storage per machine, and this machine has almost 2 terabytes of memory, including the in-memory swap space. So when we are running the prover, so we will never have any storage or memory issue. And we are using almost 100 CPU cores for each machine. And depending on our release schedule or the importance of the release, we kind of scale out this, and we are spending a lot of money only for testing prover and constraints before we move to deployment. So here we also have, in our prover, we also have many different modes. So we can only check constraints, or you can run partially prover. You can run partially, or you can just run the full prover, just like in production. So for the constraints only prover, for testing one trace, it takes less than 1 minute. And for the full version, it takes more than 30 minutes to test it. When we have, and also here in the shadow environment, when we have to test it, we sometimes scale out this environment to have 5 or more best nodes, and also in the prover we have 5 or 10 more machines. So depending on our release schedule, we can kind of control this. And also when we talk about the coverage of our testing, so for constraint-only testing, we cover, if it's very important major release, we cover more than 10% of the historical ranges. And then for each release, we are trying to cover more than 1,000 full proofs, generate more than 1,000 foolproof, so that we make sure that everything's ready to be deployed. And also, we usually use these ranges with max TPS and latest ranges to be sure that everything's all right. So let's talk about some lessons and discussions. Yeah, so what we learned from our testing is that a good zkEVM testing framework will always save your cost and your team because you're not testing it enough, and we just directly go to testnet or mainnet. This is disaster, right? And if you get any error from, for example, testnet, I think it will cost even more because human costs or infrastructure costs, and also your users won't be using your network for a while. So that's really bad. So we are trying to spend lots of money and effort solely on testing. And what we found, another one, is that when your network is idle, you better focus on just traces with high activity, because when you're testing over network with very low activity, it's almost meaningless. Testing over that kind of network is almost meaningless. And what we found is also testnet is not enough. So you just deploy testnet, but because your testnet will have very limited activity, so it will not find you any errors before you move to the mainnet. That could also happen. So that's why you need to build a very good testing framework. And here's some discussions. So what we thought is we need a kind of standardized or open source testing framework for better zkEVM ecosystem. And also, I thought maybe we need a very good benchmark test data so that researchers or zkEVM projects can just use it. When they build their constraints, they need some test data for testing it. And maybe this isn't just an idea. Maybe if we can build a kind of infra where you can borrow some transactions or generate traces out of other EVM compatible chains, that will be also very useful. And we are currently working on high-level language for writing constraints. So this is conclusion. So before we just deployed it and just pray for no errors. But right now, after this testing framework and testing phase, we are happy. We are always happy to deploy, and we are 100% proven since June 9th. And so far, no incident so far. So yeah, there are not many zkEVM projects out there, so I hope we can keep building together the ecosystem, and happy to collaborate with you all always. Thank you so much. We have 1 or 2 minutes, so if there's a question. Yeah.
Thank you very much for the talk. You mentioned that you have this 10% historic data that you use for testing, right? My question is, how do you pick those traces for testing? Because I mean, you can take 10% of only transfer of ERC20s.
That's correct. Yeah, I mean, yeah, that's kind of limitation, I could say. We just randomly picked 10%, including those very high TPS. Yeah, that's what we do usually.
But this doesn't guarantee completeness of the entire EVM operations, right?
Yeah, that's correct. That's why, yeah, I mean, if there is a 100% test data set, that could be perfect, right? So yeah, we are still figuring out.
Okay, just one more follow-up. So for Geth, there exists this testing suite like retest.eth that is, that verifies the VM execution. Would that be a useful thing to be used for testing here?
Yeah, well, I guess so. So when we can integrate that into our testing framework, that will be, I think, yeah, really helpful. Yeah, we'll work on that. Thank you. Yeah, thank you so much.